So, hello everyone, this is C programming again, and this time we continue our topic with chapter 5. Let's see what we have done so far. So, chapter 1, running Hello World and understanding program structures in chapter 2. We continued with chapter 3, working with basic data types, and then chapter 4, using variables and assignments, and now we are here exploring operators and expressions. So let's jump in to our topic and let's see in details what we will handle this time. So far we have seen how values are stored and stored to and from variables. Simply storing and retrieving values to and from variables, while important, is only a small part of handling values. What is far more important is the ability to manipulate values in useful ways, which corresponds to the ways we manipulate real-world values, such as adding up our restaurant bills or calculating how much farther we have to go to get to grandma's house and how much longer that way might also take. The kinds of manipulations that are reasonable to perform on one or more values depend entirely on what kinds of values they are. That is, their data types. So what makes sense for one data type may not make any sense for the other data type. Now here in this chapter we will explore the following points. So understanding expressions and operations. We continue then with exploring operations on numbers and understanding the special considerations regarding numbers. Then our third topic will be understanding how to convert values from one type to another type, so type conversion and typecasting. And then we will continue with exploring character operations and compare values, and then write a program to print out truth tables and examining a snippet that performs simple bitwise operations, and exploring the character operator, or the conditional operator, the sequence operator, the compound assignment operators. And then we finish with the examination of multiple assignment statements. And here you see also our source, so coding part. You can also download and use that as well. So what are actually expressions? Well, in simple terms, an expression is a way of computing a value. And we've seen how to do this with functions and return values. We will now turn to C's basic set of arithmetic operators for addition, subtraction, multiplication, and division, which are common in most programming languages as well. C adds to this a large number of operations that includes incrementation, decrementation, relational operators, logical operators, and bitwise manipulation. C further extends assignment operations in useful way. And also C includes some unusual operators that are not commonly found in other languages, such as conditional and sequence operators. The expressions we will explore here consist of one or more values as variables or constants combined with the help of operators. Expressions can be complete statements, and just as often, expressions are components of complex statements. Operators work on one or more expressions, Well, an expression can be simple or complex as well. And for example, 5 is a literal expression that evaluates to the value of 5. 5 plus 8 is an arithmetic expression of two simple expressions, literal constants, so which with the additional operator evaluates to 13. And the more complex expression would be 5 plus 8 minus 10 is really two binary arithmetic operations where 5 and 8 are first evaluated to produce an intermediate result, and then 10 will be subtracted from that. 5 as an expression statement that evaluates to 5 and then moves on to the next statement. A more useful version would be like a value equal 5, which is really two expressions, the evaluation of 5 and the assignment of the value to the a value variable. Each value of an expression can be one of the following. So literal, constant, you see here, a variable or constant variable, a returned value from a function call. An example expression using all of these would be, for example, 5 plus a value and feet to inches 3.5. Also consider the following. The next one, a length, is we'll store the value as a variable of 5 and added a value and the function result with the parameter 3.5. The addition of function call result to the intermediate result and the assignment of the intermediate result to the length variable as well. Okay, so we got it. And this way, the different values are evaluated and are added to the length variable. Instead of one assignment, 3. And instead of a temporary intermediate result, the results of the additions are accumulated explicitly in the length variable as a result of each statement. We can continue now with a simple program that applies each method of using simple and complex expressions as it follows. So we continue with our file here, actually, with the programming. And the simple program called length.c that applies each method of using simple and complex expression goes this way. So let's do that quickly. Let's open up our file. Okay. And as I said, let's do it quickly. Include stdio h. Then the next one is we will get 1 feet 2 inches double feet function, and we also get our main function as usual with a return 0 at the end. Good. Then here int inches feet times 12 and return inches. And I think we are good. And now let's do int main int a value, which goes with 8. So 8 will be saved in int value, int a value variable, and 0 will be saved in int a length variable. Now let's go to the next step. A length is equal 5 times a value plus feed 2 inches 3.5 as parameter. Calculated length is going to be %d and new line, and a length is the value of the decimal here. And we take the next one step-by-step procedure. This time a length is going to be now 5. So we update our variable a length, and we keep updating our variable step by step. A length plus a value, then a length will be after that a length plus feed 2 inches 3.5, and then printf basically the same here, so we can simply just copy paste it. So what you see here is first a length is 5, then a length is taking the value 8 plus 5, so it's going to be 13 as I see well, and 13 plus feet to inches, we see it here, so let's calculate it again. So feet to inches, that is 3.5 times 12 is 42. Okay, so here we get then based on 42 plus 13, 55, and again here 5, so 5 plus 8 plus 42, so again, if I'm not wrong, 55. And one more time. So this program calculates the a length from the sum of a literal value, which in this case 5, a variable, a value, and the result of the feet to inches function, and then prints out the result to the terminal. The program itself isn't very useful. We have no idea what we are calculating, nor do we know why the values that were chosen are significant to us. They are actually not. For now, let's just focus on the expression a length. So the a length variable that has a value calculated by adding 3 other values together in one complex statement, and again with 3 simple statements. So now that we created, we can also run our file, and we should get the result as you see here, calculated length 55. And as you see, the single statement for calculating a length is far less verbose than using the 3 statements to do so. However, neither approach is incorrect, nor is one method always preferred over the other. When calculations are relatively small and simple, the first method might be clearer and more appropriate. On the other hand, when calculations become much more complex, the second method might make sense through each step of the computation because that would be clearer and more appropriate. Choosing which method to employ can be a challenge as you are trying to find a balance between brevity and clarity. Let's continue with introducing operations on numbers this time. The basic arithmetic operators on numbers are addition, subtraction, multiplication, and division. They are binary operations as they work on one pair of expressions at a time. They work largely as you would expect them to for both integers, so whole numbers, and real numbers as well. Divisions for the real numbers result in real numbers. Divisions for two whole numbers also result in a whole number. Any possible fraction part will be discarded. There is also a modulo operator, so modulo operator, that will provide the integer remainder of the division of two integers. For example, 12.0 divided by 5.0, two real numbers evaluated to 2.5, whereas if I use the two integers like 12 and 5 without the 0.0, then I'm going to get 2 as a result. If we were working only with integers and we needed the remainder of 12 divided by 5, we would use a remainder operator, so modulo as well. Thus, 12 modulo 5 evaluates to another integer 2. Many languages have an exponent operator. C actually doesn't have it. To raise an expression to a power, standard C provides the library function PO. The prototype for this function is double PO, so double X, double Y, which raises the value of X to the power of value Y and yields double as the result. To use this function in your program, we will need to include math.h header as well. Let's open up a new file. Let's start programming. Include stdio h and include math h. So then from here we continue with int main again, void return 0, and let's try to print out the values. Int, let's take 5 this time, int a 5, and int b 2. We can also use 3, it's okay. So the result of d powered by %d is d, that is, let's say a, b, and pow ab, right? Should be correct. Let's see if it is giving the result which we wanted, and obviously there is something wrong. I don't get it. That means perhaps I should change this value first to integer, so give the chance to update this. No. So this isn't the one which I need. Then let's see if now it would work. Come on. So this is too much here. Good. Then let's check this time. And we got it. We got it. This is correct now. Good. So this is one option. Or the other option, we just keep this one and we say 0f. So 0 float. And we run it. And we get exactly the same you see here correctly. So this is it. This is what we need to do if we would like to power the number. So, and we needed the mat.h header file, and we didn't need to write a new function prototype for that. Now let's create a new file, convert temperature.c, where we will create two useful functions, Celsius to Fahrenheit and Fahrenheit to Celsius. Okay, so one more time, a new program, convert temperature C. So convert temperature C. Let's see our convert temperature C. So convert temperature C, and then here we go, include stdio, not J. So we need two function prototypes. Double Celsius to Fahrenheit. Please keep the snake case for using the function identifier. Double degrees C, and we did the same, but this time double Fahrenheit to Celsius, double degrees F. Good. Then we need to have our int main, which you can use later. So let's write that later. We need the double Celsius Fahrenheit, this one. Double degree Celsius C, and here we return the Fahrenheit value, so return degrees F, and the other function, and this one here, is going to take the opposite way, return degrees in Celsius. So we got that too. Good. Then two more things we have to do to the calculations. So double degrees F is going to be degrees C times 9.0 divided by 5.0 and add it 32 to this value. We got the next one too. Double degrees C with degrees, degrees F minus 32 times 5.0 divided by 9.0, and don't forget the semicolon at the end. And then we need our main function this time. So we got here INTC, which is going to be, let's say, 0 degree, INTF, which is going to be 32 degrees. And now let's print F. So 4D Celsius is percentage 4D Fahrenheit. Okay, and then we got here first Celsius and then INT Celsius to Fahrenheit C, right? Now we could basically copy this and say the following. So 4D Fahrenheit is 4D Celsius, and here F and F. Let's try to look at it if it works for us. And the name of the program is convert temperature. So convert temperature C, and let's see if it works. Okay, I have a trouble here. Let's check this one more time. And yes, I got exactly what I wanted, so I'm all good. What I can still do is the following. Let's see how it works this time. Yep, exactly this is what I wanted, so that our degrees are below each other. That's why I use tab here, and I use tab here as well. Good. Obviously I can update this Celsius, so INT C is going to be this time, let's say 100, and F is going to be 200. This is just comma. And then I could use the same again, so print F, 4 digits of decimals. So for D Celsius is, and let's set the tab, for D Fahrenheit. Again, we use \n, and then here C, and then INT Celsius to Fahrenheit, and C here. Okay, and I can basically take the same line again with the difference so Fahrenheit. I got the tab also inside, so I'm good. Celsius, and this time it's going to be F and F again. It doesn't give me the chance to use it, so let's try to do it now. What's wrong? Redefinition of F. Okay, I think I know the problem. It's things that I'm going to redefine two of these variables, and I don't, and now it's correct. So they work completely correctly. Everything is fine this time. So that's it. We can continue from here again with some expressions and also explanations. Each function takes a double value type as an input parameter. We just realized it here, right? Double. And returns a converted value as double. There are a couple of things to take note of regarding these functions. First, we could have made them single line functions by combining the two statements in each function body into one as follows. So this one and this one. Many programmers would do that as well. However, as your programming skills advance, this actually becomes a needless practice. It doesn't really save much of anything, and it makes debugging with a debugger far more difficult and time-consuming. Many programmers are further tempted to turn these functions into defined macro symbols. So as follows, yeah, we could also do that. So basically you take this function and you would do define as C2F X, and then you would say X minus, so F to C X minus 32 times 5. Okay, good. So, and then you would perhaps do this. And then you would perhaps use instance, so Celsius to Fahrenheit, F to C, you would perhaps use it in a different way. Now, using macros can be dangerous because we could lose type information, or the other or the operations in such a macro might not be appropriate for the type of value given. Furthermore, we would have to be extremely careful about how we craft such preprocessor symbols to avoid unexpected results. Therefore, as you see, it already says, please don't do it. And for the few characters of typing saved, neither the single line complex returns statement nor the macro definitions are worth the potential hassle. Second, we use the grouping operator, so parentheses and parentheses, to ensure our calculations are performed in the correct order. Yeah, here you see this, and here you see this. Okay, and for now, just know that anything inside the two parentheses is evaluated first. We will discuss this later in details. The next, let's see what we have. So we can now finish the program. We have finished the program, and we also run the program. We got all the results as well. Notice how we exercise our functions with known values to verify that they are correct. Well, here I did not do it correctly. So I need to do 212 to be able to get 100 degree. 100 Celsius is 200. Okay, we got some kind of problem here. So let me check it correctly one more time. Double Celsius, yeah. So 4D Celsius is 4D, and it's CINT Fahrenheit to Celsius. Celsius to Fahrenheit is going to be F, okay. C to and F. 4D Celsius is 4D Fahrenheit, and it's going to be C, and integer Celsius to Fahrenheit, C. So it's going to be okay as well. F. And integer Celsius to Fahrenheit. Integer Celsius to Fahrenheit. That's the problem here. Here. These two. So Fahrenheit to Celsius. Right. This is our mistake. Now it's corrected. Yeah, we got all the correct values here. Good. That's why it was important also to check, double check. And good. Now you may be wondering how to perform the conversations if we pass values other than doubles into the function. You might even be inclined to create several functions whose only difference is the type of variables. Well, let's take a look at the convert temperature no program. This is going to be now the no program. All right, now let's see this code. And it says, try to compile it for yourself and see what kind of errors we will get. You will find that in C we cannot overload function names, that is, use the same function name but with different parameter and return types. So you see here first double degrees, then INT. This doesn't work. This obviously doesn't work. So we could save it, and it's convert temperature no, right? And you see already here complete types of Fahrenheit to Celsius here, and complete types of Fahrenheit to Celsius. So Celsius to Fahrenheit, Fahrenheit to Celsius, all the time complete type. That is overloading function names. This is possible with other languages, but not with C. In C, each function is simply called by its name. Nothing else is used to differentiate one function call from the other. A function having one name with a given type and two parameters cannot be distinguished from another function of the same name with different type and no parameter. So we could try to embed the type names into the function names, such as Fahrenheit dBL to Celsius so double to Celsius INT, and Celsius INT to Celsius double. But this would be extremely tedious and declared and defined for all data types. Additionally, it would be extremely difficult to use in our program. Compiler errors due to mistyping the function names and even mistyping the calling parameters would be highly likely and time consuming to work through in a large or complicated program. So how does C deal with this? Well, don't fret. We will consider this very topic soon again. Considering the special issues resulting from operations on numbers is our next topic. Let's see. We got it. We cannot overload names. We got it too, and not consider special issues. We will take a look at this one now. So when performing calculations with any numbers, the possible ranges of both the inputs and outputs must be considered for each type of number. There is a limit to both its maximum values and minimum values. These are defined on each system in the C standard library for that system in the header file limits.h. And as a programmer, you must ensure that the results of any arithmetic operations are within the limits of the range for the data type specified, or your program must check for valid inputs thereby preventing invalid outputs. So there are three types of invalid outputs that will cause the C runtime to abort. Not a number, it would be an NaN or underflow and overflow. First, let's start with understanding NaN. So NaN results occurs when the result of an operation is an undefined and or an unrepresentable number. Also consider this time an equation like y is equal 1 divided by x. What is if we get x value as 0? So when then what then is the value of y as x approaches 0 from the negative side? It will become an infinite large negative value. Mathematically, this is called the discontinuity, which cannot be resolved. As we approach 0 from either direction, the result is a value that will be infinitely different when we approach from one direction or the other direction, and therefore division by 0 is mathematically undefined. In the computer, the result is going to be NaN. NaNs also occur when the data types are real, but the result of the computation is a complex number. For example, the square root of a negative number or the logarithm of a negative number. NaNs can also occur where discontinuities appear in an inverse trigonometric function. Well, let's think about underflow NaN, so not a number. Underflow occurs when the result of an arithmetic operation is smaller than the smallest value that can be represented by types specified. For integers, this would mean either a number less than 0 if the integer is unsigned, or a very large negative number if the integer is signed. For real numbers, this would be a number very, very close to 0. That is, an extremely small fraction part resulting from the division of an extremely small number by a very large number, or the multiplication of two extremely small numbers. Let's still understand overflow of not a number. So overflow occurs when the result of an arithmetic operation is greater than the greatest value that can be represented for the type specified. This would occur with both the addition and multiplication of two extremely large numbers, or the division of a very large number by an extremely small number. So we can now consider a precision. When performing calculations with real numbers, we need to be concerned with the exponential difference between two of them. when one exponent is very large and positive and the other very small negative, we will likely produce either insignificant results or an NaN, so not a number. This happens when the calculated result will either represent an insignificant change to the largest exponent value via addition and subtraction, or be outside the possible range of values through multiplication and division, and therefore, of course, not a number, so an NaN will result. Adding a very, very small value to a very, very large value may not give any significant change in the resulting value. Again, precision in the result will be lost. We can now continue exploring type conversion as well. So C provides mechanisms that allow you to convert one type of value into another type of the same value when there is no loss of precision. In other words, when the conversion of values results in the same value, so C operates without complaining. However, when there is a possible loss of precision, or if the resulting value is not identical to the original value, then the C compiler does not provide any such warning as well. So understanding implicit type conversion values is the next topic. So what happens when expressions are performed with operands or different types, for example, the multiplication of an int with a float or the subtraction of double from a short? Well, we can look at size ranges 2 from chapter 3 as well one more time. There we saw how different data types take different numbers of bytes. Some are 1 byte, some are 2 bytes, some are 4 bytes, and the most values are 8 bytes long. When C encounters an expression of mixed types, it first performs an implicit conversion of the smallest data type in bytes to match the number of the bytes in the largest data types in size, so in bytes again. This conversion occurs such that the value with the narrow range would be converted into the other with a wider range of values. That's why it is the implicit conversion. So consider the following calculation here: int feet 11, double yards 00, and yards feet divided by 3. In this calculation, both the feet and so the feet variable and the 3 literal are integer values. The resulting value of the expression is an integer. However, the integer result is implicitly converted into double upon assignment. The value of yards is 3.0, which is clearly incorrect. This error can be corrected by either typecasting with feet or by using decimal literal as follows. So here you see. The first statement casts feet to a double and then performs the division. The result is double. The second statement specifies a decimal literal which is interpreted as a double and performs the division. The result is a double. In both statements, because the result is double, there is no conversion needed upon assignments to yards. Yards now has the correct value of 3.6667. Implicit conversion also occurs when the type of the actual parameter value is different from the defined parameter type. A simple conversion is when a small type is converted to a larger type. This would include short integers being converted into long integers or floats being converted into doubles. Also consider the following here. Long int add, this function long int I1, I2, and then return I1 and I plus I2, and sign character by B1 and B2, and we got then B1, B2, 3, 1 as R1. Sorry. To add a function has two parameters, which are both long integers of 8 bytes each. Later add is called with two variables that are 1 byte each. The single byte values of 254 and 253 are implicitly converted into the wider long int when they are copied into the function parameters. The result of the addition is 507, which is correct. Most integers can easily be converted into floats or doubles. In the multiplication of int 4 bytes with a float 4 bytes, an implicit conversion will happen. Int will be converted into a float. The implicit result of the expression would be a float, obviously. In the subtraction of a double, so 8 bytes, from a short 2 bytes, conversion happens on the short. So first it is converted into a long 8 bytes, and then it is converted into a double 8 bytes. The implicit result of the expression would be a double. Depending on what happens next in a compound expression, the implicit result may be further converted. If the next operation involves an explicit type, then the implicit result will be converted into that type if necessary. Otherwise, it may again be converted into the widest possible implicit type for the next operation. Now, however, when we assign an implicit or explicit result type to a narrower type in the same assignment, a loss of precision is likely. For integers, loss involves the high order bits. A value of 32 million assigned to a character will always be 255. For real numbers, truncation and rounding occurs. Conversion from a double to a float will cause rounding or truncation depending upon the compiler implementation. Conversion from a float to an int, so integer, will cause a fractional part of the value to be lost. So consider the following statement. Here we go. The only change in this statement is the type of the R1 variable. You see that here as well. It is not a single byte. So while B1 and B2 are widened to long int and returns a long int, but this 8-byte return value must be truncated into a single byte. The value assigned to R1 is incorrect. It becomes 252. When performing complicated expressions that require a high degree of precision in the result, it is always best to perform the calculations in the widest possible data range and data type, and only at the very end convert the result into a narrower data type. Now let's test this one, trunk rounding C. We will type a new program, so let's do that as well. Let's start. Include stdio header in our file, then void. So we get two function prototypes, void double func double dbl and void long int func long int li, and then int main void. We can start with return 0 as usual, and we need to continue with our new functions first. So void double func double dbl print f double func percentage point 2f, and a new line, and it's going to be dbl. We are good. Can do the next one as well. So void long int func long int li and printf long int func ld, so long double, and new line and li as well. So we got that done, and now we can move back to our main function, say float value 58.73 and short integer int value it's going to be 13, and long int func int value and a long int func float value. And now we continue with double func float value and double func int value. So let's start to run this one and this trunk rounding. We got the file, save it, let's run it. And this is what we get at the end, as you see. So obviously we got our values here, the original values here, and long int function will just return as a truncation values. So we haven't yet explored the ways in which printf can format values. For now, we could just simply use them. Point 2f, that is the 2 decimal places, and the LD is the long INT, which I mentioned as well before. Now you can notice as well that no rounding occurs when 58.73 is converted into a long integer. However, when we do lose the fractional part, this is called the truncation. So losing the fractional part means truncation, and that is what happened. Here you go. The fractional part, so 0.73, will be cut off. And a short integer is properly converted into a double, just as a float is properly converted into a double. Also notice that when you compile the trunc rounding, no compiler error, no runtime warning will be given when the float was converted into a long integer. Now we can start using explicit type conversions, so typecasting. If you rely on implicit casting, our results may grow awry, or we may get unexpected results. To avoid this, we can cause an explicit yet temporary type change. We do this by casting. When we explicitly cast a variable to another type, its value is temporarily converted into the desired type and then used. The type of the variable and its value doesn't change. Any expression can be prefixed by type to change its explicit type to the indicated type for the lifetime of the expression. This lifetime is typically a single statement. The explicit type is never changed, nor is the value stored in that explicitly typed variable. We have an example, that is the casting C. So let's run that example now. New file, let's do it. Include stdio as usually, the header file we need. So and then int main, and then double, so return 0, and we put everything here. So int numerator and int denominator 5. Result is going to be numerator divided by denominator. Printf truncation. So %d divided by %d, %2f, 2g n, and we got numerator denominator and result here. Then the next one is result and double numerator divided by denominator. Printf no truncation, to f dot to f divided by d, resulting in Actually, I could also change this one. Point 2f and backslash n, and again we go with numerator, so double numerator. Guess it's correct in this way. We will check if it's not, then I will change later. Denominator and result. The next one is result, numerator, denominator. So basically we do this one here again, but adding here double. And now printf again, printf. Two times tab, and then d percentage d divided by percentage 0.2f, and we got the next line. As well, but before that we need a result as well, so let's add the result here, percentage 0.2f, and this is gone, this is done. Now we need is numerator, then double denominator and result. Let's try to run it, and we got here casting this time. And I'll have a problem here. So expected we got that, here we go, we have a issue. No, we got that correctly. And we got this run wrong. Okay, we got result undeclared, right? So each undeclared identifier is reported only once for each function. Let's try to take a view of this one in program is. What it says again. So result is undeclared, that's the point this time. So we need to set the double result first. Let's do it. .0, and now it's done, and now we can see what we get here. So And then let's see what, the explanation as well. Here we go. In casting C, we can see in the first division expression that there is no casting. Yeah, right. There is no casting and no implicit conversion. Therefore, the result is an int integer, and the fractional part is actually truncated. Let's see it again, that we see it well. Yeah, the fractional part is truncated. You see that here. We could perhaps add this one. Let's try to run it again. Let's see what it changes. So we got everything done this time. That looks much better, way better, good. Okay, this is exactly what I wanted, so let's run it again. There you go. So the result is an int and the fractional part is truncated. There is no 0.60. And when the int result is assigned to a double, the fractional part has already been lost. So we got here the problem. And in the second and the third division statements, we guarantee that the operation is done on double values. So you see here double, or here as well double. And by casting either one of them to double, the other value is then implicitly converted to double as well. The result is a double, so when it is assigned to a double, there is no truncation. The types of numerators and denominators are not changed permanently, but only within the context. So let's stop here and not continue from here. Let's see what we have done so far. We have started our new topic, chapter 5. It's about exploring operators and expressions, and we will finish up to the operations. So we basically write a few of the programs. Here we go. First one, what we have done is introducing operations on numbers. So what kind of operations we can do and why we do this. So one of them is a little bit complex, the other one is separated into steps, and sometimes this, sometimes the other is a better option. Then we finished with all these operations, and we also saw what 4D means in our case. So for spaces for decimal numbers, and then we talked about the number, so underflow and overflow, where it doesn't really matter what it would be, the difference. And then we also started with type conversion. We got the so-called implicit type conversion, but the explicit is the better way, because then we have no loss in our or a loss that we actually prepare in our case. But this is what we have talked about, and this is where we have talked about the truncation as well, what the truncation, so the fractional part of the value will be cut off, and that's what we call, again, truncation. And then we also saw this here. So truncation happens when we talk about the integer. So in that way, we just use the double result, and we create an integer, and not we haven't explicitly talked about it that we would like to keep our numbers as doubles. And then we continue the next time from operations on characters. Thank you very much for your attention, and let's continue later. Bye.